So what is a rectifier? So rectifier is a device that converts AC to DC. So there may be various applications of DC. For example, say you want to charge a battery. So battery basically works on DC. So you need to feed DC current to the battery in order to charge it. Now suppose in our home, the outlets we have, the electrical sockets we have, there we have AC voltage. Now suppose you want to charge a battery with that AC voltage, what we need to do is that we need to convert the AC to DC, and after conversion that DC value can be used for charging the battery. Okay, so once again, the rectifier is a device that converts. So rectifier is a device that converts AC to DC. Okay, so how half-wave rectifier device looks like? The half-wave rectifier is a very simple device, and we have been discussing in previous videos also. So suppose this is the source, this is the load. So this type of circuit we were discussing in previous videos. So this is basically a half-wave rectifier. Okay, this works as a half-wave rectifier. So how it works as a half-wave rectifier? Let's see. Suppose the input is now an AC, denoted as Vm sine omega t. Okay, suppose this is the AC input voltage. Let me draw a little clearly. Equal to say Vm sine omega t. So it will look like this is the peak value of the voltage. Okay, this is the input voltage. Okay, so suppose this is the input voltage, what will be the output voltage look like? Output voltage I basically mean is that what will be the voltage across this load, this field. Now to analyze, let's first consider the positive cycle of the AC. Okay, so suppose we are analyzing the positive cycle. So when in this condition, when positive voltage is applied, will the diode conduct or not? Obviously the diode will conduct. Again, how can we check whether the diode will conduct or not? Let's consider that the diode is not conducting. Let's consider an open circuit here, and now we are considering ideal diodes. Okay, let's not consider practical diode now, let's consider ideal diode. Suppose this is the reference. So for the diode to conduct, VA should be greater than VK. Whether VA is greater than VK in this circuit, let's check. What is VA? VA is equal to VAO, and this is positive. See, this is positive. And what is VK? VK is VKO. As the diode is not conducting, this is an open circuit condition, current is 0. So basically the node the node reference node and the cathode terminal basically at the same potential, it's 0 volt. So here VA is greater than VK, diode will conduct, no problem. And when the diode conducts, how the output voltage will look like during the positive cycle? it will conduct, current will flow. So VL, it will also be like this. Okay. Fine. Now what will happen when the curve input voltage takes a turn, that is the negative cycle? So when the input voltage is now negative here, when the input is negative, let's again check whether the diode will conduct or not. So now what will be VA? VA is VAO, it will be negative. This is now like this, right, with the negative cycle. So VAO is negative, and again VKO is 0 volt. So here VK is greater than VA, so that won't allow current to flow, and it is a reverse biased condition. So what will be the load voltage now? Now the load voltage will be, let's suppose this input voltage, the time period, let's consider as t. Here it will be t by 2, t by 2. Okay, so from t by 2 to t, there will be no voltage because the diode is not allowing the current to pass from when the input was positive. Okay, so how the voltage across the load will look like when, so this is t by 2, this is t. So during the negative half cycle, the diode won't allow the current to pass. So what will be the voltage across the load? It will be 0 during that condition. Okay, so this will be 0 during this condition, and when there was a positive cycle, we have the voltage here. So if we combine the positive and negative cycle, how the characteristic will look like? So suppose this is the input voltage, suppose this is the input voltage. Okay, how the voltage across the load will look like, or the output of the rectifier. Within the positive cycle, fine, no problem, it will be exactly the same as the input, but during the negative cycle it will be 0. Again, when there is a positive cycle, it will be like this. Okay, so this is the output of half wave rectifier. This is the input voltage. Okay, so to summarize, if input is like this, so to summarize, suppose this is the input, this is the input, this is the output. If the input looks like this, how the output will look like? It will look like this. Okay, this is pulsating DC. Fine. Now see, so when we talk about DC, what shape do we have in mind? So when we say DC, so what we mean by DC is that it should look like this, right? This is ideal DC. Okay, but in our circuit, what were we getting? We are getting like this. Obviously, this is also DC, but it's not up to our expectation, right? Our expectation is that the output should look like this, an ideal DC. But instead, we are getting some pulsating DC. That is, we have some kind of ripples here. Okay, so with half wave rectifier, this kind of ripples will be there. So we have an index that is called ripple factor, which basically says how much ripple is there in the output of a rectifier. Okay, the best case is the ideal DC, it should look like this, but with half wave rectifier, our output will look like this. Okay, so suppose we want to quantify, means how much the output of the rectifier is deviating from the ideal case. So we can use this index called the ripple factor, and it determines how much ripples we have in the output of the rectifier. Lower the ripple, it's better. Okay, so what is, by definition, what is ripple factor? The ripple factor is it's a ratio of RMS value of AC component by DC component. Okay, this is the definition. So ripple factor is the ratio of the RMS value of the AC component by DC component. Means where the AC component in the output of the rectifier out so ripple factor by definition is, ripple factor is a ratio of the RMS value of the AC component to the DC component. So RMS value of the AC component in the waveform, this is the output waveform of the rectifier to the DC component of the output waveform of the rectifier. Okay, this is the output waveform of the rectifier. So if we write the ripple factor formula, there is formula of the ripple factor. This ripple factor is denoted by this symbol. Okay, so it's like a gamma. So this is the ripple factor. So the formula is Vrms by Vdc whole square minus 1 take root. So this is the formula of the ripple factor. So what is Vrms? Vrms means the RMS voltage of the output waveform of the rectifier. And what is Vdc? Vdc is the average value of the waveform. What is which waveform? The rectifier outputs, obviously. So basically we need to calculate the Vrms of the rectifier output and the Vdc of the rectifier output. So Vdc is nothing but the V average, the average value of the waveform. Now let's calculate the ripple factor for an ideal case. So what was the ideal case? The ideal case is that the output voltage of a rectifier should look like this. Obviously this kind of waveform we can't obtain from half wave rectifier. From half wave rectifier we can obtain like this. Okay, just for now forget about this half wave rectifier. Suppose we have a rectifier circuit, we have a very good rectifier circuit, and the output voltage of that rectifier circuit looks like this. Okay, suppose 10 volt. Now obviously just by looking at this waveform we can see there are no ripples. Okay, but let's still calculate the ripple voltage. What was the formula of the ripple voltage? Vrms by V average. Okay, whenever we use the term Vdc, it basically means V average, means the average value square minus 1. Okay, this was the formula ripple voltage. Now let's calculate the RMS value of this waveform. So what will be the RMS voltage of this waveform? So the RMS value will be 1 by time period 0 time period. Suppose with this Vdc. Okay, so let's calculate the RMS value of the voltage of this waveform. Okay, what will be the RMS value of this waveform? It will look like, what is the formula of RMS voltage? 1 by time period 0 to t V square Now let's calculate the RMS value of this waveform. So what will be the RMS value of this waveform? RMS value we can calculate like this. So 10 Okay. So RMS value of this waveform is 10 volt. So what will be the average voltage, average value of the voltage, so average value will be 1 by time period 0 to t and dt. So it will be 10 volt. So what will be the ripple voltage now? Ripple voltage is the RMS by average. RMS is 10, average is 10, whole square minus 1 is equal to 0. Okay. So as expected, there are no ripples in this waveform and the ripple factor is 0. Fine. Okay. Now let's check the ripple factor of the half wave rectifier output. So basically, let's find the ripple factor for this waveform. So let's consider this omega t. So this is will be twice pi, this will be pi. Similarly here it will be twice pi. Okay. So what will be the RMS voltage? RMS voltage will be, this is the total time period 0 to, the signal, that is the waveform, exists only up to pi. Out of this time period 0 to twice pi, the signal exists only up to pi. So we will integrate up to pi and it will be Vm sine omega t whole square d omega t. Okay, root over. Let's break it down. It will be Vm square sin twice pi is equal to 0, sin 0 is equal to 0, then ultimately we have this. So what will be value? Vm by 2. This is the RMS voltage of the half wave rectified output. Okay. So next, to find the ripple voltage, we also need to find the average voltage, average value of the waveform output voltage of the half wave rectifier. So this is our waveform. So what is the average value? Average value will be simply 1 by twice pi here integration 0 to pi Vm sin omega t. Okay, this is the average waveform, average value of the waveform. Cos looks like this. So what is cos pi? Cos pi is -1. -1, and what is cos 0? Cot 0 is also 1. So it will be Vm by pi. Okay, this is the average value of the half wave rectified output. So if we now calculate the ripple factor, what will be the ripple factor? Vrms by V average whole square minus 1. The RMS voltage was Vm by 2. This was the RMS voltage. RMS voltage Vm by 2. And what is the average voltage? Vm by pi. Okay. So now if you calculate, you will get the ripple voltage approximately 1.21. Okay, so in terms of percentage, ripple factor is equal to 121%. So in the ideal case, when there was a constant value, the ripple factor was 0. Obviously there was no ripple, but in half wave rectifier circuit, by waveform only you can notice that there are ripples. But if you want to quantitatively check what is the ripple percentage, so it's 121%, or ripple value is 1.21. okay, it's quite a high value. There's a high amount of ripple present in the high wave rectifier circuit. Fine. So after ripple factor, we have one more index which we called as the conversion efficiency. Okay, conversion efficiency. So what is the value formula of the conversion efficiency? It is P dc by PSC. What is P dc and PSC? This is DC output power, this is AC output power. Okay, and DC output power, this is calculated using average value of current. If current calculated using average value, this AC output power, this is calculated using RMS value. Suppose this is a half wave rectifier. Obviously we have an input to the half wave rectifier like this, and output will be like this. Okay, now suppose the output of the half wave rectifier is connected to some kind of load, suppose an R load. Okay, this is only the circuit of the rectifier. Suppose this is the R load, this is the rectifier output, this is the rectifier input. Okay, so suppose this is the current. So here DC output power, who consumes the output power? By resistor. Okay, and what is the formula of the power absorbed by the resistance? It is I square R. Okay, so this line, the DC output power calculated using average value, basically means we need to consider I average here, and when we tell AC output power, again who consumes the power in here in this circuit? Obviously the rectifier. But now as is written here, the AC output power is calculated using the RMS value. Okay, so AC output power will be I RMS whole square into R. Okay, so what will be the conversion efficiency of half wave rectifier? It will be, see what was the formula? It's PDC by PAC, and this is the P average square R, and this is the I average square R, and this will be the I RMS square R. Okay, sir, will get cancelled. See, what will the average value of the current? The current will also look like this. This one, if the load, the voltage across the load looks like this, and this is purely R resistive circuit, the current also takes the shape of the voltage. Obviously the magnitude will be different, but the shape will be same. This is the current of the half wave rectifier. So what will be this RMS value of this current? RMS value of this current will be, again, will be IM, this is IM by 2. Okay, and what will be the average value of this current waveform? Average value of this current will be Im by pi. Fine. Then what will be the conversion efficiency? I average square Im square by pi square divided by IRMS square, that is Im by 2. If you square it, it will look like this, means 4 by pi square conversion efficiency, and it will be approximately 40.6%. So the conversion efficiency of half wave rectifier is 40.6%.